Welcome to Textbook Engineering Problem, where we explore complex engineering problems and discuss different methods for solving them. In this video, I'll be breaking down a problem and discussing different ways to tackle it. However, keep in mind that there is no one correct path for some of these solutions, and I encourage you to share your own insights and thoughts in the comments. Together, we can learn and improve our problem-solving skills. So, sit back, grab a notebook, and let's dive into today's problem. Today we're working on Elementary Principles of Chemical Processes 3rd edition, and we're doing problem number 3.37. The problem statement says, the chemical reactor shown below has a cover, called a head, that is held in place by a series of bolts. The head is made of stainless steel. Specific gravity equals 8.0. Is 3 inches thick, has a diameter of 24 inches, and covers and seals an opening 20 inches in diameter. During turnaround, when the reactor is taken out of service for cleaning and repair, the head was removed by an operator who thought the reactor had been depressurized using a standard venting procedure. However, the pressure gauge had been damaged in an earlier process upset. The reactor pressure had exceeded the upper limit of the gauge, and instead of being depressurized completely, the vessel was under a gauge pressure of 30 psi. Part A, what force, in pounds force, were the bolts exerting on the head before they were removed? Hint, don't forget that a pressure is exerted on the top of the head by the atmosphere. What happened when the last bolt was removed by the operator? Justify your predictions by estimating the initial acceleration of the head upon removal of the last bolt. Okay, so this is the picture that they gave to us here. I've kind of copied that here, and so it gives us all the dimensions that we'll need in our calculations. And then we've also got the specific gravity of the steel that they used. Let's take a look at the force balance on the head. Okay, so for our force balance on the head, we have the weight of the head here. We have the pressure inside the reactor pushing on the head times the cross-sectional area of the opening. Then we have the atmospheric pressure of the atmosphere pushing down on the head, as well as the bolts pushing down on the head. Okay, so that's our force balance, and this is our force balance, and it should add to 0 because the head is stationary. And from this equation we can calculate what the bolt force is. Let's take a look at the weight. We know that the weight is equal to mass times acceleration due to gravity. We can calculate the volume of the head, and we were given the specific gravity of the head. So we know the density from the specific gravity, and we can calculate what the volume is from the dimensions they gave to us. The pressure of the gas inside of the reactor has a gauge pressure of 30 psi, so we also need to add on top of that. That's 30 psi above atmosphere, so we need to add an atmosphere to that. Also, we have an atmosphere of pressure pushing down on the head. That's P naught. The cross-sectional areas that these pressures apply to are a little different because the outside of the head is larger than the inside of the head exposed to the high pressure. And so we have a little bit of a difference in the two areas that the pressures are exposed to. Okay, so here we calculate what the force of the bolts are. We just plug in all of these equations that we have. We have the pressures multiplied by their respective areas, pressure multiplied by its respective area, and this will give us pounds force. And then we have this long conversion for the density, the weight of the head itself. So we've got the volume of the head portion, we've got the density portion, and then we've just got conversions. Also, we've got the gravity, acceleration due to gravity, and then we've got finally the another conversion in order to get it into pounds force instead of newtons. Okay, So when we calculate all of these, we see that the different forces are equal to these, and then we calculate our total pounds force here. So we've got about 7,000 pounds of force pushing up onto that head. So now we say, okay, now we've removed all the bolts, so we don't have a bolt force anymore. What's the initial acceleration of the head? Well, we know what the total force is on the head. It's 7,000 pounds. So we've got a total force pushing up on this head of 7,000 pounds. What's the initial acceleration? Okay, we know that force equals mass times acceleration. So we know that mass is equal to volume times density. So we calculate what the volume times density of the head is again, and divide that by 7,000. Or 7,000 divided by that will give us the acceleration. So that's what we have here. We've got our force, convert that into newtons. This is the volume of the head in inches cubed, and this is the density of the steel. Then we do our conversion factors, and we're left with meters per second squared. So it's traveling 100 meters per second per second. So it's got a very high acceleration. Basically, the head shoots off like a cannonball. And we have a high pressured gas leak coming out of the reactor. So we don't really know how much volume is in the reactor, so this could be potentially a lot of gas pouring out of this reactor. We don't know if the gas is poisonous. We don't know if it has the same oxygen content as air does, so there's a potential asphyxiation risk as well if something like this happens. Okay, so those are some pretty dangerous conditions. Alright, so for part B, it says propose an alteration in the turnaround procedure to prevent reoccurrence of an incident of this kind. Okay, so two alterations that I thought of that you can make is you could put a redundant gauge used only on the bleed line. So whenever you're bleeding off the reactor, that line has its own pressure gauge, and you only use that pressure gauge when you're bleeding the line. That would prevent that line from being used when the reactor was in operation, and prevent it from being damaged during the normal reactor operation like the other gauge was. And so in order to use that, you could situate valves in such a way on that line that you could tell what the pressure is in the tank when you needed to. The other thing you could do is you could change the vent procedure to calculate, to allow for a certain amount of time to have elapsed while you're bleeding off the pressure of that reactor. And you could do a calculation that looks at, okay, how much pressure, how much material do we think is in this tank, or how much material do we know is in this tank from our operation, and under certain accident scenario, if the tank is overpressurized, how much would we think is in that tank, and then you can estimate how much time should elapse while you're bleeding that tank in order to know that the tank has reached atmospheric pressure. And then you could put a safety factor on that time. And so then you could give an operator and say, hey, it takes a full 3 hours for this tank to bleed off. And so when the operator goes to vent the line and he's only vented it for half an hour and the gauge shows that it's 0, but he's only vented for half an hour, he could say, hey, the procedure says I'm supposed to let this vent for 3 hours, even though the gauge says that the pressure is 0. So you have to let it vent for a full 3 hours, and you could mandate that happens procedurally, and then that could also potentially catch pressure gauge malfunction as well. All right, well, that is it for problem number 3.37. Thank you for watching, and I hope you found this video helpful in your problem-solving journey. Remember, there are other routes you can take to arrive at the same correct answer, and I encourage you to leave a comment with any additional insights or questions you may have. Also, if you have any specific engineering problems you would like me to cover, please let me know in the comments. Your feedback is valuable, and I look forward to continuing the conversation with you. don't forget to like and subscribe for more engineering problem solving videos. Thanks again, and I'll see you in the next video.